So my name is Chuck Rhoades. I am a senior manager of digital infrastructure for Pizza Hut. And today, I'm going to be talking to you about microservices, born, raised, and growing on Google Cloud. And so for us, this is really a customer journey. So we started working on building out our service infrastructure on Google Cloud last summer, so about a year ago, and we've been able to do a lot in that time and move forward. So as it's a journey, we'll kind of talk through it in those phases. So to start with, we had a plan. We wanted to build a microservice mesh using containerized architecture in a public cloud environment. And so as we started that, we knew there were a few key things we wanted to do. So we wanted to use Kubernetes for orchestration. And since this is a Google conference, I'll just go right ahead and assume that we've all agreed that Kubernetes is the best orchestration tool. But we did do our research. We didn't just start there. We looked at other options. We looked at other technologies. And we really found Kubernetes to be the best of breed for serving public workloads, private workloads, and all the things that we were going to need to do in our architecture. Next, we were going to be writing microservices in Go. Again, Google conference, so I'll assume we all know Go is the best programming language. But I'm not trying to start a fight there, so it's totally okay if you disagree with me. But we really felt like Go has a lot of synergies with container architectures that made it a really great fit. So the ability to compile down to single binaries that you can deploy into a container, it makes your images really small, it makes your deployments really small, and it lets you be very efficient in how you're deploying those containers into your architecture. Finally, we had settled on deploying to Google Cloud. There were a lot of reasons for that. There were a lot of things that went into it. But key among those was just simply Google Kubernetes Engine, which a year ago was called the Container Engine, but it still had a K for the name, so it works. It was really the best-in-breed way of deploying services into a public cloud environment. Not having to manage masters, not having to pay for your instances that your masters are running on, and really just the ability to have all of the latest features of Kubernetes available in a very timely manner for deploying your services. So we had a really good idea of what our core architecture was going to look like. So before we kind of moved forward, though, we really needed to think about what actually is a microservice. As I've heard this term used in a lot of different ways, and I think the meaning stays a little bit fuzzy. So as I was preparing for this talk, I really started to kind of second guess my own ideas about a microservice and didn't really want to be judged harshly. So I thought, let me go use Google to find out what the world says a microservice is. And I couldn't find a really great definition. I found sort of, kind of paragraphs talking around what microservices are. But I did find a set of kind of general concepts that I think most of us can agree on. Small, independent services. Generally, we're deploying those either into containers or virtual machine architectures with CI/CD pipelines. And ultimately, those services are interacting with one another through service discovery. And so those are good principles. Those are sort of good basic ways of describing a microservice architecture. But it still doesn't really define what the actual microservice is. And I think there's room there for us to have different opinions about it. But for us, the really key thing was service boundaries. Where are we drawing the service boundaries? Now, what we really found to be great guideposts were sort of two rules, right? They're not hard and fast. We can have some flexibility, but they sort of set the upper and lower boundaries on how big we're going to make an individual microservice. So we said every service should be as small as possible while maintaining meaningful business function, right? So when we're trying to break services down, I think we've probably all at some point in our career, for the software developers among us, we've made that mistake of making a service too small, and we eventually found we've just created an API that we have to write SQL in or something like that. So there is a lower boundary that is meaningful business function. But on the other side, we want to make sure that every one of those services fully and completely encapsulate the data and the function that it's responsible for. It can be easy to have some of these things sort of creep in to our service architectures where we allow our data to be interacted with by some other kind of batch process or something like that, and almost always it gets us in trouble. So we define these as sort of our guideposts. This is what we wanted to stay between for our microservice architecture. So the last thing we really had to think about before we could get started was, what kind of services are we going to build? REST is an obvious choice. It's absolutely ubiquitous. When we looked at the people who are most likely going to be consuming the services we're building, this is what they would be expecting to consume, right? They would be expecting JSON web services over REST protocols. So it was a very good, obvious target. Also, REST is well supported. I mean, we all know every programming language you probably want to use, you're going to be able to interact with a REST service pretty readily. The downside with REST, though, for us, was that there's really no standard core message contract when it comes to REST services. And fortunately, recently, OpenAPI has really sort of become a de facto way of defining those services and interacting with them, but it's still an after-the-fact specification. And we're relying on the effort of the developer and sort of our reliability to be rigorous in how we define our services to have those OpenAPI specs actually mean anything. We've probably had the experience of interacting with an API that said it was going to do one thing, and then it did something else. And it causes all sorts of bugs downstream when you're trying to consume those services. So the other option we looked at was gRPC. And we found a lot to love there. As you can probably guess at this point, message contract was really important to us. It was something we were really focused on. And so having protobufs as the definition of an RPC be kind of the core piece of how gRPCs are put together was a really attractive thing, right? And so if you haven't had experience with gRPC, you define those with a protobuf document. It's a very clear, concise definition. And then you use a tool called protoc to generate your stubs for servers and clients, documentation, lots of things through the plugins. And so through that, we also see great tooling around gRPC. So it was definitely something we wanted to target in our architecture. But the problem we had was it's just not as common yet, right? It's still new enough. It's still not something that every consumer who's going to pull in your service is going to be ready to deal with. And so we wanted to make sure that our services were friendly to our consumers, but we also wanted to be able to make the best technical choices in our architecture. And so this sort of leads to how we came up with just sort of a very simple overview of how we were going to approach our service mesh. We drew a big distinction between a publicly exposed API and internal services in the microservice architecture. So we said for all of our services, for all of our business logic, really the meaningful bits of what we're doing, we're going to keep those as gRPC services, and we're going to put those behind cluster IP services in Kubernetes. So if you're familiar with that, cluster IP services are only available within the cluster, which means it's not exposed. There's no public IP accessibility, but all of those services can talk to one another, service discovery works, all of those things. And then we're going to build a separate kind of service in our cluster for our REST servers that is based off of an OpenAPI specification, that is a REST API that we can expose via a load balancer server out to the rest of the world. The other nice benefit we get in that arrangement is each of those individual gRPC servers can fully encapsulate the data they're responsible for, so we can follow our service boundary rules, meaning they have all of sort of the administrative endpoints and functionality in them. But whenever we create those REST servers and we define that in OpenAPI, we can only pull up the methods that we actually want to expose out to a broader audience. So this was our idea. This is where we wanted to go. And we felt like we had a really solid plan. So the next step on our journey, we had a project. Location, location, location. So hopefully everyone in this room shops with Pizza Hut all the time, and you buy our products online a lot. And so as I talk through this, it'll sort of make sense, and you'll kind of recognize it in your experience. But our customers need to be able to find stores online whenever they want to place an order with us. And at this point in time, when this project came to my team, we were at a place where Pizza Hut was in a transition. We were moving away from a previous mapping provider over to Google Maps for all of our geocoding and customer address lookup and things like that. it provided an opportunity for us to also retire an older service that we were using to help with some of that store location and delivery lookup stuff and replace that. So that was our project. When we bring projects into our team, we really like to look at it from a few specific questions. And we start with the customer, right? What do our customers need to be able to do? And for this service, they need to be able to do two things. Find all the stores in range of a particular location and find a single store that will deliver pizza to their location. So these are the two kind of methods that we see evolving out of this project. And then we look at the aspects of the service. What attributes are really important? And this is where we kind of look at usage patterns and traffic patterns on the service. So for this one, we need to return answers really fast, right? We have a very high read load because those customers are searching for their location. That's being looked up. We also need high availability. This is the first step to a customer interacting with us online. We want to make sure that's really available and really present, and we don't interrupt that ability to place orders with us. And finally, we have a low read load for the service. We only need to update data about once an hour. Our service is not the system of record for the things that it's using. It's really serving as an online accessibility point and more of a cache. So we took that service architecture we started with, and we said, okay, how do we break down this service we need to build? The first thing was our service boundaries, right? So we started looking at what RPCs are we going to implement, and we decided we would have two. We would have one that's focused on store information, so all of the things you need to know when you find your store as far as where it is or what's its phone number, and a separate one that would be focused on location type data. So this would be the thing that's doing our geo queries and handling that information. And when you look at it, you may say, well, it's all really still about stores, so why isn't this one service? And we had that debate internally, and actually in an early prototype, it was one service. But again, we look kind of back at our service boundaries and how we want to define those, and we said, we want to make the services as small as we can while maintaining business function. So we can break these in two, so we're going to go ahead and do that. So we had two back-end RPC services supporting all the methods that we need to interact with our data. And then we pulled up those two functions, right, finding your delivery store and finding stores near a particular location into our REST API. But no service works without data behind it. So we needed to solve for data storage. And I've been around for a little while, long enough to go from talking about graybeards to having a lot of gray in my beard. So I definitely come from that architectural approach where, you know, we would start with just one database and we kind of throw everything at it and kind of torque every use case we had to fit an RDBMS system and things like that. So we didn't want to do that here. We're in the cloud now. We should be able to do things in a different way. So we wanted to pick our data storage solution based on the requirements we had. So we said we need high-speed reads. We have queries that are going to be very key-centric, right? Our location service is taking care of kind of indexing and a lot of the geospatial stuff and really gets us down to a point where we're just doing very key-centric reads. So we need something that can handle that really well. And then we need multi-region scale. Again, high availability for our customers. We want to make sure that whatever data solution we're using has that same availability kind of thing to it, right? So as we looked at the options that were out there, we also looked at some of the other offerings in Google Cloud, right? We're only using Kubernetes Engine at this point. And Datastore actually solved really a lot of the main concerns we had. It will scale to hundreds of thousands of read operations per second, so that definitely will cover the scale we need. The key query performance is amazingly fast, and so that was going to be a really good fit. And it's just multi-region built in, right? Whenever you provision out your data store, you choose a multi-region region, and you're up and running, and you have multi-region support. So we added Datastore to the back end of our cluster. We're kind of starting to pick up steam now, right? We have a full solution. We actually send queries to it. We can do things with it. But we need to think about how are we going to get our data in? And so this is really, like I said, this is a journey. We didn't know everything going in. When we looked at Kubernetes Engine, we were really only looking at it from sort of that very specific lane of I'm going to have queries coming in from the web. I need to service those and return those. We weren't thinking about other kinds of workloads. So we knew we can put our source data into a cloud storage bucket, but how are we going to get it loaded into our databases? And that's where, fortunately, as we looked through Kubernetes, we found there's a workload specifically for that. Kubernetes has the concept of a job. And so we could simply create that job. We could schedule it to run. And one of the great side effects of that was being that the job is running in cluster, we don't have to worry about extending the methods that job needs to operate outside of the cluster boundary. So that worked out for us really well. But then we needed to think about API management. So we have a service that ultimately we are going to be exposing publicly, and we are going to have consumers outside of Pizza Hut hitting, so we need the proper security and management around that. For this particular service, we were going to use API keys as the appropriate way of securing the API. But we also wanted support for JWT tokens. We knew that we would be building services that we would have kind of a higher need for authorization on. We also wanted usage reports and performance statistics to know what's happening with the services we're using them. And we want to integrate with those open API specs. We made such a big deal about having that message contract. We want to make sure whatever API management platform we're using integrates with that. Again, we looked at the service offerings in Google Cloud. We compared that to other options, and we really settled on Cloud Endpoints as being a really great fit for where we were in building and working on our API platform. So Cloud Endpoints has a really, really flexible set of security options. It's configured declaratively, obviously supports API keys, it supports JWT tokens, and it has pluggable backends, so you can use Google's auth for that, you can use your own. There's a rich dashboard integrated directly into your cloud console for your Cloud Endpoints. So you can very easily look at usage by API keys, you can see the performance statistics across your API endpoints, and a lot of the things we needed to see. And finally, it is configured and deployed with open API specs. So just by tweaking a couple of things in a couple of places on our API specifications, we were able to just immediately deploy the Cloud Endpoint. I do want to zoom in a little bit on one of the workloads we've been talking about, though. So that REST service that we have deployed, when we look at the kind of Kubernetes components of that, we have a Kubernetes service that's a load balancer targeting port 443. And then we have a REST API, a Kubernetes deployment. And at the time, we just had a single service in the pod, right? Our REST server that we built. The great thing with implementing Cloud Endpoints was it was really just a pretty minor change to that workload. You add a declaration for the ESP container to your pod. So, and the ESP is the extensible service proxy. That's actually the component that implements Cloud Endpoints. And then we just made a little port adjustment, so our REST server is on a separate port that's only available on the pod. And then the service container can proxy to it. We're only exposing the service through a protected channel, and we didn't really have to change our architecture that much, right? We just added endpoints to our REST containers, and we were in good shape and ready to go. So, next up, we needed to think about high availability. So we've kind of talked about how we crafted the cluster and how we put that together, but we're still really only talking about a single cluster. We needed better availability than that. So we said, first of all, we can use a multi-availability zone cluster. That's a feature of Google Kubernetes Engine where you can extend your cluster into separate availability zones, and it will distribute your pods accordingly so that you have availability across all of those zones. At the time we were doing this, regional clusters were not a thing yet, which are now, and that's probably what we would do and what we actually will do going forward. But even that, we're still in a single region, and you're still leaving yourself a certain amount of exposure anytime you're building architecture in a single cloud region. So what we really wanted was to have multi-AZ clusters in multi-region, right? So we have east, we have west, we have across availability zones. But when we do that, we need a way to get traffic into those zones, or into those regions. Unfortunately, we don't have the ability to do cross-regional clustering quite yet, so we needed something that would distribute that traffic. And if you've been using Google Cloud for long, you'll probably predict kind of where we're going with this. But we needed to be able to distribute traffic into our cluster. We also wanted to make sure that we're serving customers from the closest cluster to them, right? So for geographic availability, you can be served, for in San Fran, out of a data center on the East Coast, but we'd rather that not be the case if it doesn't have to be. And finally, we need to remove unhealthy clusters from the services automatically. So Google Load Balancer, or the global load balancer, solved this. And it really was just a direct fit for the use case we had, right? It's designed for, multi-region load balancing. It distributes load geographically to the nearest backend by default, and it has support for health checks, so you can make sure that your services come in and go out, or your backends for your services as the health profile changes. So we put the Google Cloud global load balancer. I always say the Google Cloud load balancer, but we put the global load balancer in front of our clusters, and ultimately, so our architecture starts to look like this. Now, we did have to make one change. Today, the global load balancer does not really recognize the Kubernetes cluster as a thing, so it recognizes it as instance pools of compute, right? So the way around that is to create a node port service in Kubernetes that the cloud load balancer can address. Fortunately, that's really pretty straightforward to do. You create your node port service. We left our load balancer service in place because we found it was still beneficial to be able to route traffic directly to regions or for testing and seeing what's going on there. But it got us to this point where we had sort of fully rationalized and fleshed out architecture. So we implemented it and we turned it on. And it worked really well. It actually served traffic really well. This was in place last year through Super Bowl, which is our Super Bowl. A lot of businesses talk about like what day of the year is their Super Bowl. For Pizza Hut, it is actually the Super Bowl. So this did a really great job. It performed really well. The architecture scaled as we hoped and expected it would. But along the way, what did we learn? And the answer would be a lot, right? We learned a lot of things. And I think most of what I've been talking about up to this point really was us learning as we went, right? Learning that we needed API management. What was that going to look like? Learning about needing load balancing. What is that going to look like? But I really want to highlight a few specific things, sort of from, we were right, we learned, to we were wrong. And so we'll start with we were right, because it's always great to start on a high note. gRPCs with well-defined service boundaries worked really, really well. So as of right now, we are going through a lot of upgrades and some feature changes to some of those early services we built. And what we've really been happy to find is that by having those service boundaries and having them written in RPCs, we can really trust those protobufs to be the thing we need to target. So, the experience a lot of us as software developers have had of just implement the interface and your implementation will be fine. Mostly. We do get the ability to carry that into our service architecture. So we can say, implement the protobuf and then do all your performance and load testing and everything you need. But you can trust that your consumers are going to be okay because you implemented the protobuf. So that worked really, really well. What we were kind of pleased, I don't know if surprised is the right word, maybe delighted, but StackDriver actually turned out to be a really amazing tool set for us. We knew in a distributed architecture, we're going to need to be able to know what's going on with our services and how's everything performing, right? So having StackDriver logging and tracing available was really a huge benefit to us. From the very beginning, we were structuring our logs so that when they did hit whatever downstream log system they would go to, they would be searchable and accessible. The integration between Kubernetes Engine to StackDriver, though, just sort of made all that work, right? We just write the log out like we always would with whatever components we want, and they show up in StackDriver fully broken down so that we can search, we can create metrics and do all those things. And then tracing, we did see that we needed to do distributed trace from the beginning, so we said, we'll implement this, we'll put it in all our services, and we'll wrap all of our callouts in a trace boundary. And we'll be able to kind of see how the service is performing, right? And so it was kind of cool to look at the charts and pull it in at the beginning, and so it was kind of fun. But then we noticed on one of the services in particular that about a third of the traffic was significantly more latent than the rest of the traffic in the service. And so much so that it was really noticeable, right? When we looked at the performance graph, you sort of had these two peaks. There was one big glut of all the traffic and then like 100 millisecond delay in a second peak. And so that was problematic. Why is a third of our traffic so much slower than the other traffic? And the good news was it was really easy to find out, right? We just simply went in and we clicked on a few of the traces, and fortunately we had wrapped the problem area in a boundary. And so we saw there was a call out, right? There was a place in that service where under certain conditions, we would call to geocode a particular piece of information. And it was something that was cacheable. It wasn't really customer specific, but it's one of those situations where because it was sort of downstream of so many other things, it had just kind of gotten wrapped in a library, and we didn't really count the cost of the call anymore. But through tracing, we were able to identify it. We switched that over so that we did properly cache that response. And we got rid of that second peak and moved all of our traffic back together. So from there, we loved tracing even more. And then we noticed, actually, it's better than we thought, right? Because tracing is great across our services, but it also integrates to cloud endpoints, and it integrates to Datastore. So now I have a very rich amount of detail all the way from the point where traffic enters into my endpoint, what Cloud Endpoints does with it, what latency that introduces, all the way through my architecture, and then what's happening in the database, which is a really wonderful amount of visibility into what's going on with our services. And finally, we also learned that our REST layer that we talked about, it does work. It lets us do the things we wanted to do as far as pulling services up out of the RPCs for exposing those to public, but it gets a bit boilerplate-ish. Most of the time as we're implementing that, we're sort of just recreating a call, an open API that we already created in protobuf and passing it through. And developers love writing boilerplate, so we left it in place for a while. But then they told me I was wrong. They don't love writing boilerplate, so we started looking at other solutions. And that kind of takes us into where are we going from here, right? So where are we going? We have several different areas that we're looking into now. So one of those is Istio. And if you're looking for me during the conference, go to any of the Istio talks. You'll probably find me there because I'm attending as many as I can. We really think Istio is going to be an amazing expansion to what we do in container architectures. So if you've worked in Kubernetes, you know it does do a really great job of managing services, but there are still some things you're doing yourself or some things that are left to the developer to implement, right? So Istio solves a lot of those challenges. So one of the things just with proxying traffic throughout your cluster, if you implement an architecture like we have, you'll see gRPC is an HTTP2 service. And so some of you may have been thinking as going, like, how did you solve that problem of proxying gRPC traffic inside of Kubernetes? And with a lot of work, that's how we solved it. Istio has that built in, right? It is HTTP2 aware whenever it's distributing traffic inside of the cluster. And so that's a really huge benefit. The other thing is once you have an architecture sort of scaled out the way ours is, you start to have routing at a lot of different places, right? You have some DNS stuff going on. You have some routing in your global load balancer. Each of your Kubernetes load balancers are implementing their own load balancer, and so you have routing in that. And you ultimately kind of have how your services are routing to and through the clusters is a little bit kind of spread around. With Istio, you can declare all of that routing in cluster and have it really take care of managing everything once it makes it into the mesh ingress. And finally, mutual TLS for service-to-service authentication. So we've really been looking a lot at how we're doing defense in depth and where we want to go with that. And Istio just meshes in really well with what we want to achieve there. Next, so we talked about that problem of having those sort of REST APIs. And the main use case we had for that was we need to be able to kind of cherry pick specific methods out of RPCs, mix those together, and sometimes transform the request and responses away from what we would do in the RPC to something that's more specific to a particular consumer. And so really what I've described there is a lot of what Apogee actually does. So as we've matured our services and we've looked at moving into a little bit more of a full-featured API management suite, we're moving in that direction. And so again, as I was talking about gRPC and REST, some of you guys probably thought about, why didn't you look at the gRPC gateway? Because that's pretty much what it does, right? It takes your protobuf, it compiles out a REST proxy for that. And so that's actually the direction we're going to be going now. So we'll be wrapping everything in gRPC gateway proxies. That will expose those as APIs up into our Apogee layer. And then from there, we will be able to pick which endpoints we want. We'll combine those into products within Apogee and do the transformations and all of the things we need to do there. And then where else are we going? More and more and more and more services. So I really kind of talked through a use case with 2 services. We've grown well past that. We've had several other projects where we've introduced many additional services. We look a little bit more like that initial map, right, where Not everything is just a service exposed through a REST. We have things that are purely internal to the cluster. We have things that are wrapping calls out to the broader world. We've actually brought in other cloud products, so I didn't have a chance in this particular use case to talk about Cloud PubSub, but that's become a really significant part of our architecture as well. We found anywhere that we needed to do an asynchronous payload, it's fit extremely well into what we're putting together and how we're approaching things.